Today, what I will explain you is we're talking about the for loop impedance. So this is the supply, this is the equipment. So from the supply to the equipment, this is we call the external resistance, and inside the supply, the impedance is internal impedance. So there are two kinds of the impedance: external impedance and the internal impedance. So the impedance value for the calculators are for loop impedance. So the for loop impedance total F for loop. This means that when the electrical fault happens, the current coming through the both are external internal element and go to the ground. So this is why that we calculate the total F for loop impedance is ZS. ZS can be equal to the U0 by IA. In this case, U0 is a nominal phase voltage. IA is a current causing the automatic operation of the protective devices. Therefore, this IA value can be determined. It's depending on the type of the circuit breaker. Type B circuit breaker, IA is a 4-type rated current of the circuit breaker. Type C circuit breaker, IA equal to 7.5 type rated current of the circuit breaker. Type D circuit breaker, IA equal to 12.5 type rated circuit of the current circuit breaker. So this is the ways how we calculate the IA. So if you know the IA, you can calculate the for loop impedance. So therefore, if we calculate this, we also need to calculate the maximum demand. The maximum demand is depending on the cable selection. So in this case, our cable selection depends on the arrangement of the circuit, length of the circuit, and the socket outlet circuit. So they are the depending on the which equipment are the included in the circuit, how to arrange the circuit, and also the length of the circuits. So depending on those circuit arrangement, we have to select the cable. In the mid-type cable selection, also depending on the for loop impedance, also the for loop protection. So that's why those are things are have to be concerned to determine the wiring circuit diagram design. So based on those facts, we design a wiring circuit diagram. Then if you get this wiring circuit diagram, then depend on the wiring circuit diagram, we can draw the single line diagram, and then we can do the connection diagram. So this is a typical circuit diagram. This is line 1, line 2, line 3, and a neutral wire. So the line 1 is connected to the active base switch and connected to the equipment and connected to neutral. And this is us I connected to ground. So neutral us are connected by the MBM, the main active neutral system. Now we have to connect it. And cable impedance we have to calculate. When you use a cable impedance, depending on the cable impedance, we have to select the ES3008. So table 34 to 39, we have to follow the ES3008, table 34 to 39, and we can calculate the cable impedance. So the best equation is R equal to RCL by 1000. R is the resistance of the cable ohm. RC is the table value. So this impedance value you can get from the table 34 to 39. Depending on the type of the cable, you can determine the cable impedance. And also this is the weight of the table value ohm per kilometer as the length of the cable. Then you calculate this RC equal to divided by RC equal to RC. R equal to RCL divided by 1000, then we can calculate the table impedance. So this is the ES3000. We show the tables are 34 to 39. So table 34 to 39 we go through. So table 34 is a single core cable, copper cable, aluminum cable, depending on the conductor cross-section area, we calculate the table impedance 45 to 90 degrees centigrade. And also the table 35, this is multi-core cable, copper conductor, aluminum conductor, we can calculate the table impedance. And table 36 is a multi-core cable, sheets are multi-core with the shaped conductors. So this is for the cable type, and depending on the copper and aluminum, depending on the conductor size, we calculate the cable impedance, ranging from the 45 degrees centigrade to 90 degrees centigrade. Table 37 also, flexible cross and a flexible cable with copper conductor. We calculate the cable impedance. And table 38 is MIMS cable, metallic sheet cable, mineral insulated metallic sheet cable. So we calculate the temperature, conductor temperature, and the cross-sectional area. We calculate the cable impedance. And also the 39 single core area bell or the insulated conductor, depending on the copper and aluminum as a material, we calculate the cable impedance. So this is the ways of how we calculate the cable impedance. Cable impedance. So that we have to calculate this characteristic AC resistance. We need to calculate characteristic AC resistance of the single core conductor. In the 45 meter less of the 10 millimeter square 4 core and the others cable, so 4C plus E V90 copper conductor. So in this case, there will be the table 34 single core, table 35 multi-core circular shape, table 36 multi-core and the shaped conductor, table 37 flexible, table 38 is MIMS, table 39 is single core area bare conductor. So the across there's a problem given the is the 4 core and the others, so that this is the multi-core. So we have to select that table 35. So table 35, 10 millimeter square and 90 degrees centigrade. So table 35 we select here, 10 millimeter square and 90 degrees centigrade. Table 35, go back here. 10 millimeter square and 90 degrees centigrade. Here you got 2.33. Substitute 2.33. RC equal 2.33. Then R equal to RC by 1000. RC 2.33. Then is given the 45 meter and divided by 1000. You got 0.1050. And then this one we also we calculate. This is for the cable impedance. So this is the way we calculate the external resistance depending on the cable. And also the internal outflow impedance can be calculated. ZIND is equal to 0.8 U0 divided by IE. So that's equation. U0 is nominal voltage, IE the circuit breaker operating current, and this Z internal impedance you can calculate by this way. So this problem we find out here. Outflow impedance. We need to calculate the maximum permissible outflow impedance, ZIND of the current supplying the hot water service type C. Service type C is a 20 ampere magnetic circuit breaker in 230/400 volts installation. If this circuit is wired in the 3.75 millimeter square 2 core plus arc V90 orange circular cable and the length of the cable is 16 meter. We need to determine the impedance of the cable between the active and the protected earthing conductors, and does this circuit comply with the ES3000 or not? Calculate the voltage drop of this section of the cable. So those they have to be calculated. So firstly we have to calculate the ZIND 0.8 U0 by IE. In this case, U0 is a phase voltage 230 volt, and also the IE is this is a type C circuit breaker 7.5 times fault current. In this case, 20 ampere. 20 ampere is an MCV current. This one multiplies 7.5 because of the type C. So the I equal to type C circuit breaker current multiplies 7.5. This is the rule. So that by substituting the formula, we got a 1 by 2270. Cable resistance must be less than the ZIND to comply with the ES3000. And leakage circuit breaker we work. This is the rule. When you calculate the deck cable resistance, it must be less than the calculated value ZIND. So if the cable resistance is less than this value, and circuit breaker will be working. So this is the way so firstly we calculate the ZIND, so then we got the 1 by 2270. Then we also need to calculate the cable resistance. Cable resistance is a multi-core cable, 2 core plus arc. So in this case, a multi-core cable, we have to use a table 35. Table 35, and also the cross-sectional area is 2.5 millimeter square, temperature is 90 degrees centigrade. So this is the way we have to know about. The temperature is V90, 2.5 millimeter square, 2 core plus E. So this is the 2 core, so multi-core cable, 2.5 millimeter square is a cross-sectional area, V90 is a temperature 90 degrees centigrade. So that we shall select the table 35. So 90 degrees centigrade, 2.5 millimeter square. So this is table 35. copper conductor 90 is 2.5 millimeter square. Here you got the 9.45. So 9.45 you get it. We substitute 9.45. And length of the cable. Length is a 16 meter. Substitute a 16 meter and divide by 1000. So you got the 1.134. So the internal resistance is 1.227. External cable resistance is a 1.134. Therefore, this resistance value is less than the internal impedance. So it's comply with the ASR 3000. So if also comply with the ASR 3000 and unleakage circuit breaker will be working. If we calculate the cable resistance value is greater than the ZIND, it will not comply with the ASR 3000. So unleakage circuit breaker will not be working. So this is the importance of you select the appropriate internal impedance and the cable resistance. Whether the circuit breaker will be working or not at the time of the unleakage condition. So therefore, we need to comply with cable resistance must be less than ZIND so that it will comply with the ASR 3000 and unleakage circuit breaker will be working when the unleakage fault happens. So this depends on the different other problem we have to calculate. So multi-go cable, another thing are two-go cable. Those things we have to calculate. Those programs are also given. The next one is a maximum length of the conductor. How long the cable you should draw to comply with the ASR 3000 rule. So this is the maximum length of the conductor. Any circuit, how long you should draw the cable. So this is the maximum length. So L maximum depending on this equation, 0.8 multiplied U0 SPH SPE divided by IA rho SPH plus SPE. L maximum is a maximum roulette in the meter. U0 is a nominal phase voltage. Rho is a resistivity. In this case, our copper resistivity 22.5 into 10 power minus 3 ohm millimeter square by meter. IA is a current causing the instantaneous operation of the circuit breaker. SPA is a cross-sectional area of active conductor. SPA is a cross-sectional area of the protected earthen conductor. So that those are the given the information whether how long you can draw the maximum length of the conductor. So based on this information, we calculate this problem. Calculate the maximum rule length. This is a cross-sectional area 4 millimeter square. 2 plus earth conductor V90. So the circuit is supplying the good dogs are protected by the C25 ampere clip are MCB into the discharge of 400 volts installation. In this case, U0 is 234, SBA is 4 millimeter square, and IA is 25 millimeter square. This is the type MCB, so 7.5 die to 25 ampere. And then we have to calculate the SPE. So in this case, we have to find out the what should be the phase conductor. SBH and SBE. SBA is crossing the area of the active conductor. SBE is a crossing the area of the earthen conductor. So these problems are to calculate the maximum. We already know that this equation we have to substitute. U0 we know it. SBA we know it, but SBE we haven't know it. IA value, we already calculated the IA value. This is 7.5925. And rho also we know that copper, this is 25. Copper is this value is given as 22.5 into 10 power minus 3 ohm millimeter square meter. So those things are you calculate. So we have to find out the SPE. SPE is protected as a conductor. So in this case, the conductor side, depending on the active conductor side, we refer the table 5/1. So we have to find out the table 5/1 of the ASR 3000. So we open the ASR 3000, we find the table 5/1. So go back and find the table 5/1. So this is table 5 by 1. So table 5 by 1, this is the cross-sectional area of actin. This is cross-sectional area of the copper actin gonada. This is aluminum actin gonada. So the cross-sectional area is actin gonada given the 4 millimeter square. Because of 4 millimeter square, we find out the 4 here. So this is the 2.5 millimeter square. Gonada size 2.5 millimeter square. So therefore, we substitute in this formula 2.5 in the place of the SPE. In the place of the SPH is a 4. Then we calculate the 67 meter. So the maximum length of the gonada should be the 67 meter. You should not draw them more than 67 meter. If you did, it will not. It will also overheating the cable. Also, it will not protect it against a gonada. Affordably will not be working. So this is for the point of the supply. Consumer main, here main switch board, here is sun main, 400 ampere, and distribution board and the load. So this is the arrangement of the your circuit. In this case, this is a 100 millimeter square. So this is given the information. So this cross-sectional area of the cable is 100 millimeter square. So that will be the copper conductor is given, line to phase, line, active, and then phase and the arc conductor included. And they are arranged with the 3.5, and the IZ value is a 403 ampere. And this is a maximum demand 150 ampere. That is a 300 meter. And also the fault current rating of the circuit breaker is an 8-time circuit breaker rating. So the information. So in this case, we have to follow this thing. IB is less than IN less than the IZ. So maximum demand current is an IB 150 ampere. IN is a protected by rating. Protected by rating given a 400 ampere. IN 400 ampere. And the IZ value will have to be calculated. IZ is a for loops are for current can be calculated. So in this case, the for loop current also the 403 ampere is given. So in this case, it complies with the ES3000 because the informations are the IZ 403 ampere when the fault current happen, and also the IN is a protected by rating, and IB is a maximum demand current. So it's comply with the ES3000. And also we also need to calculate the body draw. Body draw is calculated at VCLI by 1000. It does not say that the number of go, that's so that we have to assume that single go cable. Cable 40 had to be utilized. So the cross-sectional area of cable 100 millimeter square, temperature 90 degrees centigrade. So therefore, cable 40 of the ES3008 have to be calculated, utilized. So this is that we find out the cable 40. Cable 40 of the ES3008. So the 150 millimeter square. Then we have here we see about the temperature. Temperature 90 degrees centigrade, 100 millimeter square, 0.316. How to get here? 150 millimeter square temperature 90, so that this is 0.316. So this like 0.316 is a this one is our VC value. VC 0.316. Length of the cable is we calculate the length of the cable is 300 millimeter, 300 meter, and also the current maximum demand current 150 substitute, and then you got the 40 by 22 volt we got. So in this case, this 40 by 22 volt is less than 5%. 5% of the supply voltage 400 volt, 5 is 20 volt. So the 5% of supply voltage is 20 volt. We calculate the voltage draw is 40 by 22 volt. So this is less than 5%. So this is acceptable. Then we also have to calculate the maximum length of the maximum length of the design, this system. So we substitute here ZIND equal to U0 by IA. 0.8 U0 IA. So 0.8 U0 is a 230. IA is a maximum current we calculate is a IA is a 400 ampere. This is a when you got it for current. So this IA is a 400 ampere. 8 multiply circular rating. The circular rating we got. So 8 multiply circular rating, you got the here is 400. So this 400 shall substitute here. So 8 into 400, so you got the 0.05750. So you need to compare with the K-value system. So in this case, this is a ZINT is a 0.0575. So we have to find out the K-value system. Whether it comply with the circuit breaker EL3000 or not, whether upper circuit is a protect or not. So ZINT 0.8 U0 by IA, that formula. So 0.8 multiplied 230, 8 into IA value is a circuit breaker rating is a IA value. So this will be the substitute the 400 volt ampere. The current wiring rating. So this is the 400. IM value 400. So IM value is 400 here. So we calculated IM 400 ampere. This is a protected device rating because here given 400 ampere is given. So this 400 ampere we substitute here. Here this 400 ampere we substitute and 8 times. So because of the magnetic circuit breaker, so 8 times the 400. So this is the IA value. U0 is a 230 volt. So 0.05750. This is a ZINT. This ZINT need to be compared with the K-value system. So K-value system is called the active wire and the out wire. Because of that, from the active wire going through, current going through the active wire and going back into the out wire. So therefore, the total K-value system is active wire and out wire. Current will be flowing through. Current flowing through the active wire, then go to the passing through the equipment and go back to the earth by passing through the out wire. This is why we have to calculate the active wire and the out wire. So the active wire side is the impedance need to be calculated. Out wire impedance need to be calculated. Active wire impedance is a 150 millimeter square cross sectional area given. This is single core. Single core, therefore we utilize the table 34, 90 degrees centigrade and 150 millimeter square. So we find out the tables are 34. So because single core is a table 34. So 150 millimeter square and 90 degrees centigrade. So 0.16. So we got 0.16. So the RBA 0.16 multiplied that is a 300 and divided by 1000 you got a 0.048. And also out wire side. Out wire is not given. So therefore we have to find out the table 5 by 1. Because the active wire 150 millimeter square, out wire side need to be calculated. So we refer the EL3000 table 5 by 1. 150 millimeter square active wire, out wire side 50 millimeter square. So out wire side we got it from here 50 millimeter square. Then based on the 50 millimeter square, we refer the 34 and we find out the resistance. So that we find out the given resistance. Given 34, 50 millimeter square. So 0.4940. So this 0.494 we substitute here. So this 0.494 multiply 300. That's all the given RC by 1000. So RC 0.494 is a 300 divided by 1000. You got that 0.1842. Then we add together to the resistance RBA by RBA. So 0.048 plus 0.148. You got the 0.1962. So in this case, RC must be R must be less than RINT. RINT is a 0.575. R is a 0.1962. So this R is a not less than R ZINT is even greater. Therefore, it does not comply. It does not comply. It will not circuit breaker and leakage circuit breaker will not be working. Therefore, we have to change the internal resistance. Because of in this case, we have to find out the internal how to make the compliance. How to make the compliance? In this case, active wire side is depending on the maximum demand current. Because of the active wire, we already selected based on the maximum demand. We can only increase our wire side. Because of the because there are two resistance. Active wire, RPH, and other resistance are RPE. RPH and active wire side is cannot change. The only possible thing is we have to change the wire side. Our wire side is originally we select the 50 millimeter square, so it does not comply. So that we have to increase the wire side. So another side is increased. So the this tables are 50 millimeter square original wire. Now we 70 next one. In this case, 0.342. So that 0.342 substitute formula, and then we calculate again the resistance. So in this case, 0.342 we substitute here. So the 0.1052. Then we add it again 0.1506. So in this case, ZINT, we got it here. So this is the resistance. So therefore, we increase as a resistance as well. So in this case, ZINT is to be calculated. In this case, another thing is that we have to reduce. Circuit breaker current has to be reduced. So circuit breaker is we use as originally 400 ampere circuit breaker. So we reduce it 150 because of the after 400 there will be 150. So this 150 you calculate it ZINT 0.153. ZINT 153 we got, and here is RPH RPE. We also increase the circuit breaker side of the your given. So this is 106. So therefore the ZINT is greater than the RT. So that will be acceptable. Therefore the change has to do is instead of using the 400 ampere circuit breaker, we change to the 150 ampere circuit breaker. I think that is increased to the 70 millimeter square. Because you cannot change the active wire side because active wire is running through all the cable, all the systems. So it's impossible to change the active wire because all the drawing. Only thing you can do is you change the circuit breaker. Circuit breaker is easy to change because of the panel. You can take out the original circuit breaker, put another one. Output data side can be changed because either draws are separately. Therefore, the original 400 ampere circuit breaker and our side 50 millimeter square does not comply because alligator circuit breaker will not working. Therefore, instead of using the 400 ampere circuit breaker, we change to the 150 ampere. Based on the 150 ampere circuit breaker, we can calculate the new ZINT. This is the 0.153. And also that we increase the data side. Originally is a 50 millimeter square. We increase to the 70. So therefore, we calculate again the resistance, and then based on the load resistance, those changes are total ZRT is equal to the 0.1106. So this is less than the ZINT 0.153. Therefore, it complies and the circuit breaker will be working. So this is the ways we can do this. Today's lesson is how to maximum follow impedance, unfollow impedance, and how to change your circuit component to comply with the AS3000, whether your unleakage circuit breaker will be working or not at the time of the unleakage circuit. So therefore, today is we calculate the maximum length of the cable, also the unfollow, and also the compliance. Whether your unleakage circuit breaker will be work or not, those things I explain you in this lecture.